Welcome to Real Physics. Today I want to talk about the proton radius and its fundamental implications. Now, as you might have heard, there have been measurements that showed that the proton was significantly smaller than assumed before, just 0.84 femtometers, where everybody believed that it was much bigger. And one interesting thing from the sociology of science is here. This was discovered in 2010, while for decades all physicists believed that the proton was much bigger. And then when he came up with this new measurement, so everybody is now reconsidering his old measurements and saying, oh no, we messed something up. The correct value is 0.84, not 0.87 as believed before. Now that's one thing. The second thing to mention, also a sideline, is here. I mean, that should have tremendous impact on the entire high energy physics, because I mean, particle physicists, they do nothing else all day long than letting protons collide. They obviously, if protons are much smaller than assumed before, that should have an impact on the data analysis, but you hear nothing about that. So anyway, but who wants to understand the logic of particle physics anyway? So, but this is, as I said, also a sideline. I want to focus today on something really interesting from a fundamental point of view, and there is a coincidence. And this is very interesting. It has been noted by a couple of heterodox scientists, interestingly. And I mean, two things to mention here. Why did I insert this p/2? Because it's fairly precise now. You can argue about this is coincidence and I don't believe in numerology. Okay. But nonetheless, in any case, it remains remarkable that we have an order of magnitude coincidence of h, Planck's constant, with c, the mass of the proton, and the radius of the proton. And this is important because the proton is the only particle for which such a relation holds. And if you think about the plethora of particles in modern physics, I mean, that kind of gives the proton a special importance. And by the way, it's the only stable massive particle we have. So let's think about these fundamental things. Anyway, the reason why I made this video is because indeed the numerical coincidence is quite close if you put the factor p/2 in here. And I have covered this also in another video, but I want to give it still another twist today. So let's look at it and do a little bit of calculations. Let's play with these numbers. So first of all, again, you have, if you put it in here, the numerical value of Planck's constant, the speed of light by definition, the mass of the proton, couple of digits, and you end up with this fairly precise value. And I think it is kind of remarkable that you have these 2-3 digits of precision. Anyhow, if we now think about the coincidence and try to play around, what can we do? You can obviously multiply with c, and then what you can also do, you have hc at the left hand side, and hc can be substituted, so to speak, by electric constants if you put in the definition of the fine structure constant, because the fine structure constant is E²/2hc epsilon naught, and you can replace this hc by the electric stuff E²/epsilon naught if you put in the fine structure constant, as I did in the next line here. You see this one. So then I multiply by the electron mass, divide by p just to get it to the other side, and multiply by the gravitational constant. And we do another thing here. We multiply by the gravitational constant from the right hand side, but on the left hand side there is this hypothesis of Mach's principle and variable speed of light. I covered this in other videos, but this is a hypothesis that has been first put forward by Erwin Schrödinger in 1925 and Sharma, and it's very likely that the gravitational constant has something to do with this data of the universe. We can discuss about the factor, whether it's 6 or 4 or whatever. We had a discussion in our recent meeting in Bonn here. Anyway, I want to multiply with g on the right hand side, and on the left hand side I put this expression in blue, which is g. And now you see something interesting highlighted in the next line. This has something to do with the gravitational force between the proton and the electron, and this obviously has to do with the electrical force between proton and electron in the hydrogen atom. What is missing is just the r squared in the denominator, but if you want to compare the electric and the gravitational force, these r squared just cancels out. So what we can do in the next line here is write this as a relation of the electric and the gravitational force. And of course this is related to Dirac's numbers and Dirac's hypothesis. He came to this insight from another consideration, if you want. But at the end we have inverse of the fine structure constant and the relation of these two forces, and this is somehow related to data of the universe. And if you write it again, so you have that kind of intuitive formula. Electric divided by gravitational force would be proton electron mass ratio and fine structure constant, and all these cosmological issues. And if you again then write it directly, this is putting in directly Sharma's hypothesis about the gravitational constant being related to the masses in the universe. Again, you can debate the factor of 4, if it's 1, if it's 2, if it's 3, if it's 4, okay. But if you take this one, you just end up with this very simple intuitive formula. I really like this. And well, in this case, you see the m is a number. That means it's being normalized by the mass of the proton, and this r would also be just a number normalized by the radius of the proton. That's what we measured now very precisely. So you would end up with this fairly simple formula for the electric and the gravitational force. Or if you want to write it in yet another way, a matter of taste, to get rid of the proton-electron mass ratio, then you have 137 times the ratio of the fundamental forces, and this is just the sum of all masses in the universe divided by the respective radius, but you have to normalize this, in this case again by the proton radius and the electron mass, so you get rid of the 8036 here. Well, that's what I wanted to show, and that's of course Dirac's observation of 1938. He said that the ratio of the electric and the gravitational force is a huge number, about the order of 10 to the 39, and he suggested that this number is related to the biggest and the smallest distance in the universe, the biggest and the smallest time scale in the universe, which is of course the radius of the universe and the radius of the proton. And well, that's more or less what you have here in this sum, but I guess in a more intuitive, in a more suggestive way that might lead us to new insights. In general, we must wonder about these coincidences. They have led physics to real insight, such as Weber's and Kirchhoff's speculations about the speed of light and relating it to the electric and magnetic constants, or as Johann Jakob Balmer's speculations about the atomic spectra, which started atomic physics. We need to wonder about these fundamental issues. If you enjoyed the video, don't forget to like it, and if you're interested in fundamental questions of physics, subscribe to this channel.